You glance down at your wrist. Heart rate, blood oxygen, a number you just trust without a second thought. But for over a year, the blood oxygen feature on newly sold Apple Watches was federally illegal to activate in the United States. The FDA didn't step in because the sensor was unsafe. Instead, a federal trade court issued an import ban because they agreed with a smaller medical device company that Apple had built this feature using stolen patents. The data we rely on to monitor our bodies is governed just as heavily by cutthroat corporate litigation as it is by medical science. The rival company is Masimo. Joe Kiani founded the business in his garage in 1989 and built it into a global hospital pulse oximetry supplier. Masimo alleges that Apple engaged them in early partnership discussions, abruptly walked away, hired dozens of Masimo engineers, and then independently launched a remarkably similar blood oxygen tracking feature. That allegation triggered a brutal legal stalemate. In October 2023, the International Trade Commission issued the import ban. To keep selling watches in the US, Apple disabled the blood oxygen app entirely via software in January 2024. Even after Apple rolled out a redesigned version in 2025, a brand new investigation was immediately opened. Yet a separate 2024 jury found that Masimo's own consumer watch infringed on Apple's design patents. The result is a messy corporate deadlock, leaving everyday users caught in the crossfire. To understand why the watch is so heavily contested, we have to look inside the wrist. Your smartwatch measures heart rate using photoplethysmography, or PPG. It shines green LEDs into the skin and measures the light reflecting back up off your blood flow as an optical proxy for your actual pulse. In controlled clinical studies, this method reaches over 99% agreement with medical chest straps when you are completely at rest. But introduce intense physical movement, and those light vectors scatter. That chaotic optical noise forces the watch's software to aggressively filter the signal to guess your heart rate. The physical vulnerabilities pile up fast. Cold hands constrict surface blood vessels. A loose strap breaks the seal. Most critically, melanin absorbs the exact wavelengths of light the sensor relies on. The higher the melanin concentration in the skin, the worse the signal quality becomes. Your resting heart rate on screen is a highly conditional optical estimate. Step outside those ideal physical parameters, and the accuracy degrades immediately. To get direct electrical data, smartwatches rely on a single lead ECG. Touching the digital crown completes a single circuit across your arms. This is a massive upgrade over optical light estimates, but it operates entirely differently from the dense web of a 12-lead ECG used in hospitals to precisely map heart attacks. To validate this consumer screening tool, Apple partnered with Stanford Medicine to run the Apple Heart Study, testing the device's passive irregular rhythm notification on more than 400,000 participants. The trial's massive scale proved the watch avoids triggering a flood of false alarms. During the study, only 0.5% of those participants actually received a notification. Among the subset who received an alert and then wore a continuous medical ECG patch for a week, 34% had confirmed atrial fibrillation. But because atrial fibrillation is naturally intermittent, a week-long patch might miss it. When researchers compared the watch's alerts simultaneously against the medical patch, the two agreed 84% of the time. The watch's single lead sensor is a precisely validated tool for flagging specific intermittent rhythms, but it structurally cannot map a complex cardiac event or replace a proper clinical diagnosis. That brings us back to the blood oxygen sensor at the center of the Masimo lawsuit, and a physiological flaw that implicates the entire medical device industry. In 2020, researchers at the University of Michigan analyzed pulse oximetry data. This chart visualizes the frequency of occult hypoxemia, a dangerously low true oxygen level that the device fails to flag. The study found this false reading occurred roughly 3 times more often in Black patients, at 11.7%, compared to 3.6% in white patients. This specific demographic blind spot was first documented in 1990. Melanin inherently interferes with the optical absorption principles that all pulse oximeters use, meaning this limitation exists in both consumer smartwatches and hospital-grade hardware alike. It took until 2025 for the FDA to issue formal draft guidance requiring device manufacturers to test across diverse skin tones. The historical accuracy of our health technology has been strictly limited by the demographics of the people it was tested on. If wrist-based optical sensors are so constrained by physical movement and skin pigmentation, how do you actually get gold standard data? In sports science validation studies, the reference device is often the Polar H10 chest strap. It costs about $90 and uses direct electrical measurement to achieve greater than a 0.99 correlation with medical ECT systems. Alternatively, wearing an optical band higher up on the arm bypasses the chaotic motion noise of the wrist, and smart rings provide excellent, stable resting data while you sleep. However, none of these alternative forms solve the blood oxygen skin tone bias. That optical vulnerability is a universal limitation of pulse oximetry technology itself. Spending hundreds of dollars on a premium wearable does not override basic human physiology. It merely changes where the sensor sits on your body. Consumer wearables are incredibly useful. They are rigorously validated for tracking broad fitness trends and providing basic rhythm screening. They are not validated as flawless blood oxygen monitors across all skin tones, nor can they replace clinical diagnostics. The number was never fake. It was measured a very specific way, under very specific conditions, and now you know exactly which ones.